In this video, we are going to discuss about instrumentation amplifier. So in IC form, it is available as AD521, AD524 and AD624. If you see, it can be also available as TCL7605, which is manufactured by this AD and all. It is manufactured by the analog devices. Okay. So basically it is used for to amplify the difference between the two input voltage signal, and it has having high input impedance and low output impedance, and it's having high CMR, a common mode rejection ratio, and it has high accuracy. So basically the uses of the instrumentation amplifier is to monitor and controlling of physical quantities like ECG, EMG in the industrial process for measurement and control of the temperature, humidity and light intensity, as it has low noise, low thermal and time difference. So it is useful whenever the acquisition of useful signal is difficult. So this is a block diagram of instrumentation amplifier. So first stage, this is my stage 1 and this is my stage 2. So here the stage 1, it represent voltage follower. Okay, voltage follower, and this one is a differential amplifier. Okay, this is my stage 2. Okay, so you can see why we are going for the instrumentation amplifier is if the input source to the amplifier, suppose this one, have a high output impedance or unbalanced output impedance, then we should use the instrumentation amplifier. Okay, so first let us discuss about the differential amplifier. It has a low input impedance and the gain cannot be adjusted easily. This is my above circuit. So let me consider what happens if both the signals are equal. So if I take this is VE and this is also VE, so I can write V0 is equal to, since the input to the inverting amplifier is VE, so I can write minus R2 divided by R1. This is the gain of the differential inverting amplifier into VE plus, so if this is VF, okay, so I can write VF into 1 plus R2 divided by R1. Okay, this is the gain of a non-inverting amplifier, right? So how to write VF? VF is equal to VE into R4 divided by R4 plus R3, right? So we substitute in this equation. So this is my first equation, this is my second equation. We substitute first equation into, okay, so minus R2 divided by R1 VE plus VE into R4 divided by R4 plus R3 into R1 plus R2 divided by R1. Okay. So this I can write it as minus R2 divided by R1 VE plus VE into 1 divided by 1 plus R3 divided by R4 into 1 plus R2 divided by R1. R2 by R1 is equal to R4 by R3. Okay. So if I substitute here, R2 by R1 E plus V divided by 1 by 1 plus R1 by R2, okay, into 1 plus R2 by R1. So this I can write it as minus R2 by R1 V plus V into R2 divided by R2 plus R1 into R1 plus R2 divided by R1. So this two get cancelled out. So this is equal to 0. Okay. So my since V naught is equal to 0, AC, the common mode gain, that is V naught by VCM, right? That is equal to 0. So now I am going to apply the differential signal to this differential amplifier. Okay. So if that is the case, R3, R4, R2, R1. Okay. Thank. So this is my differential. This is for common mode signal. Okay. And this is different signal. Okay. So if I different signal means I'm going to apply VD here and 0 to this one. Okay. If that is the case, I can write VG. So VG is equal to R4 into VD divided by R3 plus R4, right? So what is my V naught? V naught is equal to VG into 1 plus R2 divided by R1, right? So this is my third equation. If you substitute in the fourth equation, I will get R4 VD divided by R3 plus R4 into R1 plus R2 divided by R1, right? So this I can write it as VD divided by 1 plus R3 divided by R4, right? Into 1 plus R2 divided by R1. So we know that the condition, right? R2 divided by R1 is equal to R4 divided by R3. R2 divided by R1 is equal to R4 divided by R3. So what is my R3 divided by R4? R3 divided by R4 is nothing but R1 by R2, right? So now you solve this one. So you will get R2 divided by R2 plus R1 into VD into R1 plus R2 divided by R1, right? So this is equal to R2 divided by R1 into VD. So this is my V naught. So what is my V naught by VD? V naught by VD is equal to R2 by R1, right? So that is equal to my AD. Okay. So this is about the differential gain. Okay. So now let us discuss about the voltage follower. So you can see on the stage 1. On the stage 1, you have a voltage follower circuit, right? So this is how the circuit look like. So what happens if both the signals are equal? Okay, this is for a common mode. Okay, common mode signal. So since this two are VB, since there is a voltage follower here, you have since I have applied the negative feedback, this is nothing but VB. This is also VB. So the current flowing through this one is 0, right? So the difference between this one is 0. The current flowing through the opamp is also 0, right? And since this is also 0, this is also 0, I can write obviously this current is also equal to 0, right? So I can write this VB and this is also VB. So my VCM, right? So my common mode gain, okay, AC AC is equal to V naught by VC, right? So that is equal to both this, all the signals are equal to VB. So I can write VB by VB, that is equal to 1. Okay, this is for voltage follower signal common mode. Okay, so now let me give for the difference differential signal. So if that is the case, so I am going to apply um, this is during the differential mode. Okay, so let me take this as VD and this one as equal to 0. Okay, so this is 0 and this is VD. Okay, so if that is the case, I can write this is VD, this is also VD since it is negative feedback. So if this is 0, this is also 0, right? So I can write the current flowing through this one is I1 and this one is I2 and this one is I3. Okay, so we know that these current I1, I2 and I3 are same. Okay, so let me take this one as equal to um, VA and VB. Okay, VA and VB. Okay, so since the current I1 is equal to I2, that is equal to I3, I can write the current flowing through this one VB minus VD divided by R dash, that is equal to current flowing through this one VD minus 0 divided by RG, that is equal to 0 minus VA divided by R dash. So I can write from this two equation VB is equal to sorry, VB minus VD is equal to R dash divided by RG into VD. So this I can write it as VB is equal to 1 plus R dash by RG into VD. Okay, so if I solve these two equations, right, so I can write what is my VA? VA is equal to minus R dash divided by RG into VD. Okay, so what I supposed to get? I was supposed to get VB minus VA, right? Since the positive voltage is given to this one, so I need to get V naught is equal to 8 times VB minus VA, right? So what is what is VB minus VA now? VB minus VA is equal to 1 plus R dash divided by RG into VD plus R dash divided by RG into VD. That is equal to 1 plus 2 R dash divided by RG into VD. So now I can write what is V naught? V naught is equal to AD of VB minus VA, right? AD. So what is my VB minus VA? VB minus VA is 1 plus 2R dash divided by RG into VD. So what is AD in the first stage? AD in the first stage is R2 by R1, right? This one, right? So I now substitute here. R2 by R1 into 1 plus 2R dash divided by RG into VD. So here I have applied VD. What is VD? VD is applied only to, so this I can write it as VD minus 0, right? VD minus 0. So the VD is applied to the this one, right? If you see the signal, the VD is applied to the V2 and 0 is applied to V1. So I can write this V2 minus V1. So here you can see the instrumentation amplifier. It depends on the, if I vary the value of RG, right? So the RG is nothing but a variable resistor. So which is connected externally. Rest of the resistor are internally fabricated, right? So if I change the value of this resistance RJ, the gain of the instrumentation amplifier. So this is my gain, right? So the V naught by V2 minus V1, that is equal to R2 divided by R1 into 1 plus 2 R dash divided by RG. So if I change the value of RG, the gain of the instrumentation amplifier will get changed.